Hi, everyone. We're very happy to have Anna Beliakova for the second talk in the morning, who's going from Zurich University, who's going to tell us about algebraization of low-dimensional topology.
Thank you. Thank you so much, Hisham. So I'm very glad to be here. It's a great atmosphere, and thank you so much for organizing this event and also giving me a possibility to talk. So the topic will be this algebraization of low-dimensional topology. And so this is a joint work. So basically everything what I'm telling you today, a joint work with this guy who is Marco Dorenci, and who is now on the job market. And so it's a brilliant guy, so just don't forget him if you're looking for somebody really great. And partly the results are also in collaboration with Evelina Bobcheva and Riccardo Pergolini. So I will mention just when we will go to there. And so I'm a topologist, and in topology, so the main topic you always study is the category of cobordism. And so usually this category of cobordism, you consider kind of, so if it's n-cob, so n-dimensional cobordism, you consider n-1 dimensional, usually closed manifold as objects, and as a morphism between this object, just n-dimensional manifold, you usually use gluing as a composition, so you can have different structure on this manifold, clearly, as we have seen, for example, already for today in the morning. And also usually to make some monoidal structure in this category, what you're usually using is this disjoint union as a monoidal structure. And what I will much more use today, it's a boundary connected sum instead, because it just gives much richer algebraic structure. So, but this is just a side remark, so just let me recall, so like 2-minute summary of what was said in the talk before me, without any defects, just what is 2-cob. So here the objects are circles, the morphism are pair of pans, caps and caps, gluing it just give you a composition. And in dimension 2, so what is very nice and what you would expect, because surfaces are classified. So clearly in this case you can just immediately say who are the generating morphism of your category and what are the relation between this generating morphism. And this leads you, so clearly if you associate this as associativity, co-associativity, unit, co-unit axiom of Frobenius axiom, that what you see is actually that this well-known folklore theorem that 2-cob is actually a free monoidal category generated by so-called commutative Frobenius algebra objects. So basically, this is a statement about 2-cob. So you have just one object. This object has some prescribed morphisms. This morphism have some relation between them, and this defines you the whole category is just generated by this one. And actually, the statement also classify all 2-dimensional DQFTs. This means so all monoidal factor out from 2-cob in some vector spaces by just saying that any such factor sends this generating object, this S1, to some vector space, and this vector space needs to have the following operation, so it has multiplication, co-multiplication, unit, co-unit, and they have to satisfy the relation we have seen before. So basically, you have a theorem that this DQFT are in one-to-one correspondence with so-called commutative Frobenius algebras. Yeah, so this is completely classical stuff. This was known in, I don't know, so forever probably. And the question is, does it generalize for any higher dimension? And so I'm just introducing here graphical notation for the morphism. So the main difficulty in my talk will be that sometimes I will read the morphism from top to bottom, and sometimes from bottom to top. So for the moment I'm staying from top to bottom. So this is a multiplication, this is a co-multiplication, this is unit, and this is co-unit. Okay. So what I would like to do in this talk is to tell you that actually you can describe some cobordism categories in dimensions 3 and 4 in a very similar way to this description of of a two-dimensional manifold as a Frobenius algebras. And the idea here would be to replace Frobenius by Hopf. And Hopf algebra, it's a vector space together with a multiplication, co-multiplication, unit and co-unit. In addition, it has a new endomorphism, which is invertible endomorphism, which is called the antipode. And all these guys are subjects. So this is my graphical notation for this morphism. So it's before multiplication unit, co-multiplication co-unit, and this is the antipode. And I'm just putting the plus or minus, meaning the antipode or its inverse. And the relation are, so first of all, you have so this M and eta. It's an algebra, so you have a unit and associativity. The delta and epsilon, it's a co-algebra, so you have a co-associativity co-unit. And then you have all this together built a bi-algebra, so you have some compatibility of multiplication, co-multiplication. So this is this picture. So basically what we had before, it was a Frobenius axiom. So you would write this guy as a composition of M and delta in a different way, so like we have seen in previous talk. Or so instead of writing this as it was here, so here, in this way, yeah. Now you're writing this in this way. So this is just this one axiom. It's a compatibility condition of M and delta. So compatibility of algebra and co-algebra structure, building together a bi-algebra. And then there is some antipode axiom which actually looks like this. And there is another one. So I always not drawing the symmetric version. So if you put these things here. On the left-hand side, that you will have the same, and also perhaps so you will have some. We don't have red pen, but so you would have something like this. For example, if you co-multiply unit, then this is the same as. So I'm usually dropping the trivial axioms. But essentially I'm giving you the relations of the Hopf algebra. Okay, probably not a new word for any of you, but just let's stay like slowly develop this picture. So in fact, what I will need is not just a Frobenius algebra, sorry, not Hopf algebra, but what I will need is a Hopf algebra object in a braided monoidal category. So what does it mean? So you give me a braided monoidal category. So this is category C. So this means it has some monoidal structure given by tensor product, and you have tensor unit. And so you have an object H there, on which you have this sequence of morphisms. So for example, this is a morphism from H tensor H to H. This is a morphism from tensor unit to H. This is a morphism from H to H tensor H, and so on. This is endomorphism of H. And this morphism need to be subject to exactly the same axiom we have seen before. So for Hopf algebra, so associativity, unit axiom, antipode axiom. And the only difference is this bi-algebra axiom. So here, because now we are in a braided monoidal category, so we may not have a permutation morphism there, but what we have is a braiding. So what you use here to exchange these two strands, you just use your braiding. This is what you have, and you use. And so immediate corollary of this definition of Hopf algebra object in the braided monoidal category is that it's defined in a way that you have the first example of such object is a Hopf algebra. Can you see something? Probably not. Hopf algebra H is a braided Hopf algebra object in vect. Yeah. So this is how it is defined, because I mean, you have on vect, you have a braiding which is given by permutation, and so if you just insert here instead for this permutation as a braiding, you just immediately get the definition of the so Hopf algebra is a vector space, so it's an object in vect, and this is a braided Hopf algebra object by definition. Okay, and now clearly this is made, so the definition of this braided Hopf algebra object is made for this example to work, and the question is, do you have interesting other examples? Yeah. And this is what I would like to provide here. So I would like to construct an interesting example. This is actually due to Crane and Yetter. I think they have first observed that in this category, which I will call 3-COP0, so this is a category of connected, oriented, three-dimensional cobordisms between connected, one-punctured boundaries. So it's a huge part of just the usual three dimensions. So it's just three manifolds between whose boundary are punctured surfaces and they're connected punctured surfaces. So why I'm restricted to this case? Because in this case, so the objects are just disks with some number of handles put on these disks. So basically, you can identify objects with natural numbers, with a set of natural numbers. And now how you consider morphisms in this category. So the morphism, you consider this, for example, this is an example of a morphism from F3 to F2. So you have a disk here with the three handles, and you take, so this bottom part of this cube, you consider this as a disk with two handles in the following way. So you just look at my blue lines, and you remove a tubular neighborhood of this blue line out of this cube. And this provides you this boundary surface. It will be just a surface with two handles attached and with a negative orientation. And this is in this way, you consider this as a morphism from 3 to 2. And you basically, so in order to think about arbitrary manifolds, so basically you need to supply this manifold with a parametrization of the boundary. And you consider two such three manifolds together with parametrization to be equivalent if you have, if these manifolds are diffeomorphic, and even this, so by orientation preserving diffeomorphism, and this diffeomorphism just intertwine, restricted to the boundary, it's intertwines the parametrization. So basically, so you think about any manifold, three-dimensional manifold, but you parameterize the boundaries exactly in this way that you have this Fg upstairs, Fg prime downstairs, and you have something in between. So this is the setting. And now, so clearly it's very tiring to draw these cubes each time, and so I will, in the pictures in this lecture, I will just take a slice, like a slice, horizontal, vertical slice of this picture, and just draw this diagram in this way. And now we are coming to the main difference to the usual 3-COP, which you perhaps are more familiar with. So here your monoidal structure is not connected sum, because I would like to stay always with connected boundary, but my monoidal structure is just stacking these cubes side by side. So this is so-called boundary connected sum. So what is the main advantage of this, using this monoidal structure? So the main advantage is that now this 3-COP, so fancy speaking, it's a now it's becoming pro category. So this meaning that the set of object is isomorphic to natural numbers, and the monoidal structure corresponds just to summation of these numbers. So basically, so if I have 2 handles and 3 handles, and 2 tensor 3 is just 5 handles. And in particular, this means that the whole category is just generated by this one handle. So basically, so there is only, so it's monoidally generated by just one object, which is just one, yeah, like the natural numbers. And this is the main advantage of changing the monoidal structure, because I mean, if with the usual monoidal structure, you will have infinitely many objects which are completely unrelated to each other. So the price to pay, I do not consider cobordism between disconnected boundary, but I can completely understand, so I will give you an algebraic presentation of this 3-COP0. Okay. And what I also have to explain to you is what is a composition. So composition, perhaps, so if you're not used to this setting, it's perhaps a little bit tricky. So I draw here one morphism which is from 2 to 1, and another morphism here from 1 to 1. And I would like to compose these two and to get a morphism from 2 to 1. Okay? So how do I do this? So basically, you're just, so it's a topological construction. What you need to do, you take this handle and you embed this handle into the neighborhood of this one. This is how you glue these two cobordisms together. So you just glue it in the tubular neighborhood of this guy, but inside of this handle, I see two blue lines. So this means that so along all this path here, it will be two lines traveling around. And then after I glue this guy, I'm just putting exactly the same picture I have here. So then after gluing this guy, I'm just putting exactly the same picture. I hope I did it. Yeah, so this is the composition. Okay, and now, so this is what I promised you. So this is was observed by Krenieta and then worked out by Kerl and Lubashenko in like 90s, that the only one monoidal generator of the category. This is a braided Hopf algebra object. Okay, and here are the structure morphisms, so multiplication, co-multiplication, unit, co-unit, antipode. And it's a real fun. So I'm usually giving this to students to give them to prove their axioms. So so let me do it for you. So this is the antipode relation. And what does it mean in my setting? So remember, so I should first start here with a co-multiplication, then put here the antipode, then multiply. And then I would like to reduce this into a composition of the co-unit and unit. Okay, and if you go back to the definition, then this is my co-unit. This is my co-multiplication. Then I put this S, and I think and then I put a multiplication. So we look at this picture. So this is the first one, is a co-multiplication. Then I'm putting S, I think I put S now on this side. It doesn't matter. So I put S on the right-hand side, and then you put a multiplication. And now if you take this strand here, and you pull it up, then you see that this is a composition of co-unit and unit. So this is, okay, and in this way you can play with all the other axioms, so they all satisfy as the old fact that this is a braided Hopf algebra. And so it started so nicely in the 90s, and then it went not very far. So basically what the people immediately realized that these morphisms are actually not enough to generate all morphism in 3-COP. Because you know that every 3-manifold can be obtained by surgery on link in S3. Yeah? So this means, and this morphism actually, there is no surgery inside. So they stay embedded into R3. So say for what you need to integrate is kind of surgery component. Okay. And the surgery, so you're doing this by either inserting this integral, and so I mean these two additional morphism. So this morphism, this is a morphism from H to tensor unit. This is a morphism from tensor unit to H, so where H is your braided Hopf algebra. And topologically, this green circle just means that I'm doing surgery in the circle. And you also need this Riemann morphisms, this V and V minus 1, which are just looking like this. So if you add these morphisms, and you can see, so you add also this is just my, so I'm adding here the graphical notation in the algebra for all these morphisms. And you put the natural axioms for the integral and co-integral. So for example, this would be the system of axioms. Then you have kind of more hope to generate the whole category. So if you add this morphism, like Habiru in 2006, so he started with a different approach. So he didn't add these two morphisms, this integral and co-integral, because basically they exist. So on the level of algebra, they exist only in finite dimensional settings. So I think this was his motivation. And so instead, he was considering so-called Hopf pairing and Hopf pairing. So Hopf pairing you can define through the generate I had already. So this is a morphism like this, and Hopf pairing it's a surgery on the Hopf link. And so if you introduce this algebraic notation for this Hopf pairing and co-pairing, so they should be this Hopf pairing should be non-degenerate, meaning this zigzag axiom holds. Then the fact that it's Hopf pairing, meaning that it's exchange the multiplication, co-multiplication, and then you have some funny axiom. So in particular, this axiom for the adjoint action. Yeah. So I'm not providing full set of axiom. I'm just providing something which is really essential. And so if you now take just define as 3-alg braided monoidal category generated by a braided Hopf algebra object H, which in addition has this Riemann elements, so this Riemann morphism and Hopf pairing satisfying the axiom I listed before, then what was conjectured by Kerla around 2000 that this 3-cop should be equivalent to this braided monoidal category just generated by one single object with few generating morphism and some relation on them. So this is so-called algebraic presentation of the category of three-dimensional cobordism. And so this was conjectured by Kerla, and if you look at the axioms of which Kerla put it in his paper at that time, then actually this axiom, so this relation was lacking. So he didn't assume this relation on this adjoint action. So he just so I think he had some equivalent of those, but not this one definitely. And later, Habiru, so exactly, so perhaps it's too much here. So what I wanted to say now here, that Asayeda published a paper, I think it was 2010, claiming that Habiru has a full list of relations, and she summarized this relation. So Habiru never published anything on this. And she said that as will be soon done by Habiru, so this is hold. Yeah. So this 3-cop is equal to 3-alg, and this is proven. And probably so so I mean I don't know. So but the fact is just it was never written. And what we are doing now, so together with Marco De Renci, Evelina Bobcheva, and Pergolini, is that we are proving actually this conjecture. So I hope the preprint will be in a few months online. And so actually what we are proving, so like as I tried to explain before, there are two possibilities to define this 3-alg. So there is one possibility where using integral and co-integral as additional generators to your braided Hopf algebra generators. And there is another, which is actually initiated by Habiru, which we will call 3-alg H for Habiru. This is the one which is using pairing and co-pairing as a generator. And what we are showing that actually, so first of all, it's just completely algebraic fact that they are the same. So we are just, so they have a little bit different, exactly, they have different generating morphism, but you can construct a map from one to each other, and you can construct functor back such that it's an equivalence of categories, actually. So after we have shown this, then we prove, this is a very non-trivial thing, that both of them, it's actually equivalent to this 3-cop. That you have real algebraic understanding of the category of 3 cobordism. Okay, and what is surprising about all this is that our proof goes through 4-dimensional topology. So actually what we are doing, we're constructing some category of 4-dimensional cobordism, and we're constructing some more general algebra, and a category 4-alg, which is generated by this more general algebra, which we now call Bobcheva-Pergolini, because it was done by these two guys in 2011. And we prove the equivalence of this 4-dimensional cobordism is equal to the 4-dimensional algebraic category. And then you can pass from this 4D to 3D by taking just a boundary map, and from 4-alg to 3-alg by taking quotient by 2 additional relations, like just Kirby one move and trading of 1 handles for 2 handles. This is actually this map, so nothing surprising. And out of this you will get this statement. So this is how we proceed, and this is kind of, so usually it's very unusual proof, yeah. But this is because they were working really hard, these two guys, and they put a paper of 230 pages. So it was a single issue of a journal, just their paper on proof of. So exactly this is what they proved at the time. That this 4-cop is equal to the 4-alg. But somehow nobody believed, so I spoke with many people about this, and people didn't believe that the proof was correct. And it's hard to check 230 pages proof. And basically, so when we were writing paper about this, our referee told us that there is no single person in the world who understands branch covering and quantum algebra at the same time. So therefore, this was actually the starting point of our collaboration with them. We said, okay, let's try to get a more direct proof, and this is what I hope it will appear very soon. It's just what we are doing. We are avoiding all this branch covering. We are avoiding complicated language, and we are just trying to construct just functor from here to here, and functor. So from alg to cop, it's very easy. But what is very complicated is to construct a functor from 4-cop to the alg. And you construct some assignment of some algebra element to every this 4-dimensional cobordism. And then this assignment depends on many choices. And then you just rigorously check. It's just, this is the main difficulty. It just checks the independence of all these choices. But okay, so let us just go to 4D. Yeah, so 4D, it's not very amusing story, yeah. So it was already in the 60s, it was shown that there is no hope for any algorithm to detect diffeomorphism classes of 4-dimensional manifolds, so it's not solvable. It's the only dimension, so it's the first dimension where the smooth topological structure are going apart, and the smooth H-cobordism theorem fails. And this is also the reason why it's only in dimension 4 where the smooth Poincare conjecture is not yet done. So it's enormous complication, but we will restrict to some class of 4-dimensional manifolds, which is deal with so-called 4-dimensional two-handle bodies. So we will only deal with 4-dimensional two-handle bodies. So this means we always start with just one disk, D4, and we glue on this disk some finite number of 1 handles, so 1 4-dimensional handles. This means D1 times D3. by removing S0 times D3 from the boundary of this 4-ball and gluing this guy back. And we will have finite number of 2 handles, which are D2 times D2, where you remove from the boundary S1 times D2, solid torus, you remove the solid torus, and glue D2 times S1 on the annulus which you have here. And this results on the boundary just to surgery on this 3-sphere along the attaching map of this 2-handle. And now, so this presentation of 4-dimensional 2-handle bodies as attaching maps of some 1 and 2 handles, it should be considered subject to some moves which are actually isotopies of attaching maps, and some handle slice, and it's always handle slice of i's handles along the i's. So we will have just 1 handles over 1 handles, or 2 handles over 2 handles. And actually what you can also see is that you can reduce the sliding of 1 handles over 1 handles to the sliding of 2 handles over 2 handles. So it's actually just, so for the slidings, you just enough to consider 2 handles over 2 handles. And then you have creation and removal of canceling pairs of handles. And here, a priori, you need to consider 1, 2, and 2, 3 handles. However, we will consider, we will consider only map between 4-dimensional 2-handle bodies. So we will never go to 3-handle bodies. So therefore, we will not consider the canceling pair of 2 and 3 handles. So we will just don't because we don't have settings for 3 handles. So we just only have setting for 1 and 2 handles. So therefore, our moves reduces to so-called 2 deformations. So the 2 deformations are isotopies of attaching maps, sliding of 2 handles and 1 handles one over each other, and cancellation, so stabilization only of 1, 2 pairs, but not 2, 3 pairs. So this is the difference. So I mean, clearly maps which we consider, they induce diffeomorphism between the corresponding handle bodies, but the question is any diffeomorphism is a 2 deformation? So 2 deformations is just this subset. And this is an open problem since many, many years. So in the 60s, people tried to attack this. And actually, it was never investigated. So nobody knows. So there is no answer whether it's a proper subset, this 2 deform or not, just because of the lack of the invariance. So basically, I think we have, for the first time, we have invariants which have the potential to track these problems, because these are not a so I mean, they're actually invariants up to 2 deformations by definition, and not as usual invariant and the whole set of diffeomorphism. Okay, and so as I will come to these things later, that actually this problem of distinguishing diffeomorphism to deformation, it's closely related to Andrew Carty's conjecture, which Sergei Gukov was speaking like a few days ago. This is what was our conversation, but I will comment on this later. And so let me just define what I understand under my 4 corps. So we will call this category actually 4HB, for 4-dimensional handle bodies. And this is a braided monoidal category where the objects are connected 3-dimensional 1-handle bodies. And morphism are 2 equivalence classes of connected 4-dimensional 2-handle bodies. Again, the tensor product will be, so monoidal structure will be boundary connected sum, and the braiding is the same braiding as we before. This is just exchanging of 1 handles. So this is a picture. So this is a kind of, it's again, so you consider this as a cube. You attach this solid now 1 handles upstairs and downstairs, and on the front boundary of this cube, you draw the attaching maps for the 2 handles. You can also summarize this whole picture in a Kirby diagram. This is how usually people represent such 4-dimensional two handle bodies, so you just put, so for every such one handle, you just put a meridian, which is just a meridian of this handle, and put a dot on this meridian. So this is a Kirby presentation for the one handles. So the dotted circles, and all these circles, they are really, so these are trivial knots bounding a disk and transversally intersected by the attaching string for the two handles. So the picture is really looking like this. And you consider them up to some moves, these Kirby diagrams. And the moves, okay, let me give you the moves. So you have a sliding move for two handles, so the two handle can be slided over their two handles, so this is the usual sliding move. And the additional, the 1-2 handle cancellation looks as follows. So each time if you have attaching, so you have such a picture. So this is attaching curve for your two handles, and only this one single thing goes through the one handle. Then you can remove, so you can cancel this pair. So this is so you consider this Kirby diagram up to sliding of two handles over two handles and up to this move. Okay, so good reference for this is the book of Gomf, where it's Gomf and Stipschit. Okay, and now, so what Evelina and Ricardo did is that, so first of all, they proved that this four-dimensional handle bodies is equivalent to the category of Kirby tangles. This is basically this is just a summation of Kirby construction. So this is not very surprising. But what is very surprising is that that this is actually the free braided monoidal category generated by one single object, which is just a three-dimensional one-handle body. So it's basically solid torus. So it's just the whole category is generated by one solid torus. And this solid torus should be, we call it before, in the paper we call it four-modular Hopf algebra, but now we call it Bobcheva-Pergolini Hopf algebra. So it has some morphism. So because it's a braided Hopf algebra object, so it has clearly product, coproduct, antipode, unit and co-unit. Then in addition, it has integral, co-integral. It has also Riemann morphism. So you have like a set of generating morphism on this object, and they need to satisfy some axioms, some relation. And clearly you have all the relation you had before, so it's because it's a braided Hopf algebra, so you had all the relation of a braided Hopf algebra. But in addition, you have, for example, these two. This is the most funny relation which I have never seen before. I found their paper, so I just found their paper like a few years ago, and I was very excited about it. So for example, that you can express the positive crossing through the negative crossing and a bunch of pairing, co-pairings, antipodes, multiplication, co-multiplication, and so on. So this is an expression which relates positive and negative crossings, braidings. Yeah. So I don't know. So perhaps you have seen this. I have never seen it before. And this is a relation which basically tells you how you, I don't know, so if somebody perhaps familiar with computation quantum groups, so if you need to compute a coproduct of a Riemann element, it's a pain in the neck. Yeah, so it's basically, it goes through the whole PBV basis, it's a huge sum, so it's just nightmare. And this is a graphical interpretation of this computation, so this tells you how you propagate the Riemann twist through a co-multiplication. And this is just that. So in a way, okay. So you just add few relation additionally to what you have seen before. You call the result Bobcheva-Pergolini Hopf algebra. And the claim is that this topological category is just generated by this algebra. So you have a complete algebraic presentation of the category of four-dimensional two handle bodies. Okay. So here I'm just explaining that we are trying to write the proof of this theorem like in a more straightforward way. So what is easy to do is to go from so it's easy to take a guy here. So here the generating morphism are multiplication, co-multiplication, blah, blah, blah. And you see here already, so you take here multiplication, you send it to these Kirby tangles, which you can interpret as a four-dimensional handle body. Yeah, so it's already pictures are here. So here you take co-multiplication, so any generating morphism, basically here you need to send to the corresponding Kirby diagram and then just check the relation. This is a very easy thing. So it's again a fun. It's like the proof I showed you in the three-dimensional case. So because you immediately know. So all this morphism, so they're already explicit. What is much more complicated is if I give you arbitrary Kirby diagram here to split it into these guys. Like to find, so, and this is what was lacking before in their proof. So basically, instead of constructing, so let us call this functor phi, and so they didn't construct in the original paper this functor back. Instead, they were associating some branch surfaces to these handle bodies, and from these branch surfaces, they have a way to go here. So it was a little bit complicated procedure, and so perhaps by this reason the people didn't realize the strength of this result. But what we are doing now, so we are actually taking arbitrary Kirby diagram, and what you need to do in some sense, so because you see, so like every string of here, so like every string of a two handles are kind of doubled. So for example, braiding. So braiding it's such a Kirby diagram. So it's exchanging of two handles. So it's okay. So here you can put one handles like this. So but braiding it's essentially it's like two strands going through two strands. It's not just single strand. And in some sense, you need to, so if you have an arbitrary Kirby diagram here, you need first to double all strands in some way, which depend on how you do this. And then to this double picture, you associate an element here, so you split it into generating morphism. And this, again, depends on many choices, and we are showing that the construction is independent. But the proof will be, so I hope soon, it will be really by direct association to any Kirby tangle here, an element of the algebra. And this is a constructive proof in the sense that you can teach it to a computer or so. And you see you have a complete, so basically this algebra element which you associate to the four-dimensional manifold here, it's a complete invariant of this manifold. So for example, if you know that the map you associate in the algebra is identity, you know that here you have a four-ball.
Is the proof kind of algorithmic and uses only Kirby calculus? That's
exactly. So the proof basically, so it depends. So basically, you have, for example, this link of two handles, and what you're doing, you choose a trivialization of this link. Then you pull a band out of each component to some sum, and you basically choose a copy of each component, which is just trivialized there. You see, so these are the choices. This is how why it's related to branch coverings, yeah, because you double cover each component. Yeah.
Thank you.
Okay. So and now, so I don't know how much time do I have, but few minutes here. Okay, great. So, and then going back to 3D, it just means that you take the front boundary of your 4-dimensional two-handled bodies. You are exactly in the 3-COP. So, and to get from Kirby pictures to the pictures we had before, you just remove a dot, and you have this guy. And you add this Kirby move, and you have the theorem. So just from this big theorem here on the, between 4HB and 4ALK, you just get, it's relatively easy to get this. So what we realized with Marco is that actually, so given any unimodular Evenhoff algebra, and here I'm putting finite dimensional nullity in the definition of unimodularity. So it's mean finite dimensional unimodular Evenhoff algebra. So any quantum group satisfies this condition. So almost any. So you have a functor from this 4HB to H mod. So this means that exactly like in the 2-dimensional case, this algebraic presentation allows you to classify all 4-dimensional TQFTs in the sense by saying that, okay, so given any such guy, you have this functor. And now if your algebra is also factorizable, then this functor actually factorizes through 3 COPs. So this means that if you are working with a modular category, so what all people like Turaev and so on was all the time working with, you will never see 4-dimensional. So this is why all attempts, so starting from 94 by Turaev, then Broda, Kranieta, Roberts, Bobcheva-Messi, and so on, so they were semi-simple, non-semi-simple construction, aiming to construct interesting 4-dimensional invariant out of Riemann categories. So they mainly fail, and now we understand why. This is because they were working with modular categories which are factorizable. And also, so if you work in semi-simple setting, you also will not detect any interesting 4D phenomena. So basically what we are looking now for, it's a non-factorizable, non-semi-simple categories. So this is where you can perhaps find out the strengths of this TQFTs. And just to finish with, so this is related to this Andrew conjecture, which Sergei already mentioned, that this is about balanced presentations of the trivial group. So balance means I have as many relations as generators. So if you have such a presentation of a trivial group and you consider only moves which never change the number of, so it's always goes through the same number of generations and relations, then if you think about this group as pi1 of your 4-dimensional two-handled bodies, then this, the conjecture that you can always trivialize without adding additional relation, just through the balanced presentation. So this was a conjecture which people believe it's false, but no, since 65 there is no any counterexample. So this conjecture, oh wait a sec. So in 4D it would mean that that every 4-dimensional two-handled body, if it's diffeomorphic to the 4-ball, it's also 2 equivalent to a 4-ball. So basically, you should be able to pass from some presentation of this 4-ball to another to a trivial presentation without adding 3 handles. And this is usually, so all these potential counterexamples, they were at the beginning, they were postulated by Akbulut and Kirby as an example for exotic 4 spheres. But then it was always the same procedure, so Akbulut added somewhere a 3-dimensional, 3 ball, and then slide it very clear over the whole picture, and then at the end they have seen that actually this is not exotic, this is just an actual sphere or 4-ball. And just let me finish by saying that if you would be able to provide a counterexample to this conjecture, then you will be probably able to prove the Riemann-Slice theorem and also the generalized property R, which is generalizing this Gabay, the famous Gabay fact that every Saggiaro on the zero-frame knot, which provides S1 times S2, is actually a Saggiaro on the R knot. Thank you very much.
Thank you very much. Any questions for Anna?
So for the dimension 3, can you hear me? For dimension 3, you were categorizing these with braided Hopf algebra objects.
Algebrais, I cannot pronounce here, but it's an algebraization, it's not categorification here.
Right, and for dimension 4, it's braided braided categories in the suitable sense, right? For the 4-dimensional theorem, you had braided categories, correct? And
no.
What was
it's exactly the same. So it's it's just in both cases it's a braided monoidal category generated by just one single object, and this object has some axioms, so some to satisfy in both cases.
Okay.
So it's not going like categorical level higher, not at all. It's just the same. It just you have two more relation in 3D.
I see. Okay.
Then in 4D, that's all.
So let me continue then. So you have braided monoidal categories. That corresponds to a 4 category. A braided monoidal category is an E2 monoidal category, which is a 4 category. So you should, in principle, be able to create a framed 4D TQFT, which is fully extended out of that, but probably not all the way to the top. The usual cobordism hypothesis says that if you have a braided monoidal category, then that gives rise to a framed 4D TQFT, but typically you can't go all the way to the top. You don't have full dualizability. So you get something in dimension 0, 1, 2, but not, or 0, 1, 2, 3, but not 4. And you're seeing only 3 and 4 with the same data.
Almost, yeah. I mean, not completely, yeah, but yeah.
So that's curious, and maybe is there some relation that you have a 4D fully extended theory, but maybe not to the top, on the same data as...
So the only thing I can, so we can discuss later, yeah. So, but the only thing I can say about this, so the main difference here between this 4D and 3D is that 3D is fully dualizable. So I mean, in the sense that you have, so this Hopf pairing plays an important role, and it's non-degenerate. So you have this zigzag axiom for this Hopf pairing. Yeah, this is, and if you have this, you see all the known Rishetti derives. This is what I call this factorizable case. So if you have this, then you can forget about 4D. Yeah? And if you are in 4D, then you should look at the complementary picture. You should require this guy to be to be degenerate. And this is the only case. And this is kind of what you would like to expect, because in this case, you will, so invariance, for example, of S2 times D2 will be not invertible. This is interesting phenomenon in 4D because they should be different. This is how what you see in, for the Donaldson invariant, for example. So it just tells you that what we have seen before, like all this modular category, it's something. So you should forget few axioms there in order to be able to see something interesting in 4D. And it's interesting to find examples. So we are looking now for example for such algebras, and so we were looking. So now we can integrate unrolled quantum group, for example, in this thing. So clearly we are working with non-semi-simple construction. So restricted quantum group, we can also such things.
Okay. Any other questions? Okay, if not, let's thank Anna again for the very nice talk. Thank you.